Hey everyone, and welcome. You know, when we think about data, our minds almost always jump straight to the average. But here's the thing, the average is just one piece of the puzzle. It tells you the center, sure, but what about the rest of the picture? Today, we're diving into variance, the powerful tool that lets us see the whole story by understanding how data is actually spread out. So, here's our game plan. First up, we're going to see exactly why relying on averages alone can totally mislead you. Then, we'll get into the tools data scientists use to describe a dataset's shape. After that, we'll roll up our sleeves and actually calculate variance, tackle the super important difference between a population and a sample, and finally, we'll connect all the dots to see why understanding this spread is an absolute game changer. Okay, let's kick things off with the big problem. The average, or the mean. It tells you the center of gravity for your data, but it tells you absolutely nothing about its personality. You know? Is your data super consistent and predictable, or is it just all over the place? The average, well, it just can't answer that. To see what I mean, just look at these two datasets. On the left, dataset 1 has an average of 8, pretty straightforward. But now, look at dataset 2. Its average is, you guessed it, also 8. So, if you're only looking at the average, you might think these two datasets are basically the same. But are they really? Not a chance. When you actually look at them, they couldn't be more different. The numbers in dataset 1 are all huddled together, really close to that mean of 8. They're consistent. Dataset 2 is the exact opposite. Its values are way more scattered, stretching much farther out from the center. And this difference, this spread, is exactly what we need to measure. And that really is the core question, isn't it? We have the same average, but two completely different stories about how the data behaves. So how do we put a number on that difference? We need some kind of metric that actually captures this spread that we can so clearly see with our eyes. So how do we get beyond the simple average? Well, in statistics, we have this awesome set of tools called moments. Just think of them as a systematic way to describe the shape and the characteristics of our data. It's actually a pretty cool analogy. Just like you'd use height, width, and depth to describe a physical box, we use statistical moments to describe the shape of a dataset. It's the formal way we capture all of its key features. Now, there are 4 main moments you'll hear about. The first one, that's just the mean, our center point. The third moment, skewness, tells us if our data is kind of lopsided. The fourth, kurtosis, looks at the crazy extremes, the outliers and the tails. But the one we really care about today, the one that measures that spread, is the all-important second moment, variance. All right, let's dive deep into variance. This is the metric that's finally going to solve our problem from the beginning. It's the number that quantifies the spread we saw. So let's walk through exactly how it's calculated. Okay, the formal definition sounds a little intense, but trust me, it's not. Variance is simply the average of the squared differences from the mean. Now you might be asking, why squared? Well, there are 2 really good reasons. First, it makes all the differences positive, so points above and below the average don't just cancel each other out. And second, and this is key, it heavily penalizes outliers. Points that are way far from the average have a much bigger impact on the final number. Honestly, the best way to really get this is to just do it by hand. So let's take this simple data set of 5 numbers and calculate the variance step by step. It's a super straightforward 4-step recipe. First, we find the mean. Then, for each data point, we find out how far away it is from that mean. Third, we square all of those distances. And finally, we just take the average of those squared distances. That's it. Okay, let's fill this thing out. First, the mean of our numbers is 4.4. Now look at that third column, where we calculate the difference for each point. And notice this, if you add up that whole column, you get 0. That's just a cool property of the mean, and it's exactly why we have to square them in the next step. It gets rid of all those negative signs so they don't just cancel out. So, once we add up all those squared differences in that last column, we get a total of 25.20. This is what we call the sum of squares. We are just one step away from our final answer. All right, now for the final step, the easy part. We just need to find the average. We take our total sum of squares, that 25.20, and since we have 5 data points, we just divide by 5. And there we go, 5.04. That number right there is the variance for our data set. This single value is the measure of spread we've been looking for this whole time. But hang on, before we move on, there's a really crucial distinction we need to make. This is something that's super important in real-world data science. We have to ask ourselves, is the data we're looking at the entire universe of possibilities, or is it just a small piece of it? This is the whole idea of a population versus a sample. Think of it this way. The population is every single thing you could measure. So for example, every car that's ever rolled off a factory assembly line. A sample is the smaller group you actually have data for, say the 100 cars you pull off the line for a quality check. A measurement of the whole population is called a parameter. A measurement of just the sample is called a statistic. And here's why that matters so much. The formula actually changes a little bit. If you have the data for the entire population, you divide by the total number of items, n. But, and this is what happens most of the time, if you're just working with the smaller sample, you divide by the number of items minus 1, or n minus 1. Why? Well, it turns out that a small sample tends to underestimate the true spread of the whole population. So by dividing by a slightly smaller number, we bump up our variance estimate just a bit, making it a much more accurate guess of the real population variance. It's a tiny tweak that makes a huge difference. Okay, so we've got our variance, 5.04. But what do we actually do with that number? So what? How does knowing the spread actually help us in the real world? Here's one of the tricky things about variance. Remember how we squared all those differences? Well, that means our units are squared too. So if our original data was measuring height in meters, our variance is in meters squared. Mathematically, it's correct, but it's not very easy to wrap your head around. What even is a square meter of height? And this is why we almost always take one more step and use a related metric, the standard deviation. And it's incredibly simple. It's just the square root of the variance. By taking the square root, we get our units back to the original scale. So a variance of, say, $5.04 squared becomes a standard deviation of $2.24. Now that is a number we can actually understand and use. And this brings it all home. Why does spread matter so much? Well, it lets us spot outliers that are way far from the average. It helps us understand the consistency of a process. A small standard deviation is a good sign, a large one might mean trouble. In finance, it's a direct measure of risk and volatility. And most importantly, it solves our original problem. We now have a number that proves our two data sets were telling completely different stories, even though they had the exact same average. So, from now on, whenever you see an average, I want you to challenge it. Ask, yeah, but what's the variance? What's the standard deviation? Because now you know the real story isn't just in the center point, it's in the spread. The deepest insights are often hidden in that second moment. So what stories are you going to find?